Okay, last week we introduced polar coordinates. So I'm going to recall some stuff from there. To go from polars to rectangular, we use the identities. X equals r cos theta, y equals r sine theta, x squared plus y squared equals r squared. And then what? Y over x equals tan theta. Is that right? Yeah. Okay, and then we also said that area in polars had this r that we picked up, this little r here that you picked up, so that the area differential in polars is r dr d theta. Okay, and then we did a couple of examples on how to integrate and also how to change from rectangular to polar and back and forth like that. And so now what we want to do is just get into integration and how to do this in 3-space. So here's an example. Find the volume of the solid bounded above my favorite parabola, or to one of them, by z equals 9 minus x squared minus y squared, and below by the unit circle. So that our area of integration here is the unit circle. So okay, let's draw this. So here's our unit circle out here in 3-space. That's y, that's x, that's z. And so when x and y are 0, z is 9. When x is 0 and y is 1, z is, 8. So 8 here. So something like this. Okay, so if you're doing a double integral, what you go is you go, okay, here's r, and we have the double integral r, and then f of xy is here, dA, right? And so if we're going to do this in rectangular coordinates, so f of xy is 9 minus x squared minus y squared. dA is dx dy or dy dx, right? And then to find our limits, we go, right? We take a line array here and we go through this r, and we intersect r in 2 functions. And now we got to think, I mean, what are these functions, right? Because this guy has the equation 1 equals x squared plus y squared, so that y equals plus or minus 1 minus x squared. So downstairs it's 1 minus x squared, and upstairs it's 1 positive 1 minus x squared, and then x goes from minus 1 to 1, and these have to flip. right? Okay, I think if you think about this for 1 second, your first move is going to be to integrate with respect to y, right? So now we're going to have, I'm going to go back to black here. So now we're going to have x equals minus 1 to x equals 1. We have 9y minus x squared y minus y cubed over 3, evaluated from dx. Now think about this for a second. We're going to have to take this function and plug it in here, here, and here, and then subtract after plugging this function in. It's going to be a disaster. Okay, so let's think about this better. Let's think to ourselves, this is just a circle in polar coordinates, so it's a constant function. So now let's rewrite this volume like this, and we have our region R, and we're going to do this f of r theta r dr d theta. We're going to do this in polars. Okay. So first, let's get our limits of integration downstairs here. And if we go over here, just make a little circle. If you let r emanate L, r goes from 0 to 1, and it goes all the way around. So theta goes from 0 to 2 pi f of r theta r dr d theta. Okay, and now we need to convert f from rectangular coordinates to polar coordinates. So let me do that as a subproblem here. We have 9 minus x squared minus y squared. This equals 9 minus x squared plus y squared, and this is 9 minus r squared. And so now the integral becomes d theta. And now this is, all you have to do is the power rule a few times. Don't forget to distribute the r first, and it's actually not that bad at all. Considerably easier than what we were about to the hellfire burning nest waterfall thing here. This was going to be pretty ugly. I mean, look at it for a second. You would have to integrate 1 minus x squared to the 2/3. I don't even think you can do that. Anyways, we don't have to. So this is why we started using these polars. And yeah, it comes out nice, real nice. So let's do a guided practice problem before we meet. Using polars. Find the area of the region R bounded by the circle x squared plus y squared equals 4, the line y equals 1, and the line y equals the square root of 3x. So the x is not inside the radical, so it's y equals root 3 times x. It's actually better to write it this way, because then it's clear. And this is in the xy plane, so it's just an area problem. All right, and then we'll have some fun in class with more of these.